Okay, one more minute. Okay, I guess we should get started. Welcome. So let's quickly go through the announcements. The first web announcement is here. Instructions for assignment 4 are now posted. I just realized it's due on November 3rd, which is election day. So I'll probably change that to the Thursday because the university just requested us not to have any assignments due on election day, not the day after. So I'll probably update that and I'll make an announcement next Tuesday. But then instructions are here, so let's take a quick look at them. So the main goal of this assignment is to go over, in a little more detail of your innovation. So essentially make a technical case for your innovation. So I gave some steps here, but think of these as suggestions. Show simulations or detailed calculations. Then you can decide the metric that applies best to your team. Whether it's efficiency, amount of water per unit area, amount of power per unit area, per unit time. So whatever you want. So you have to kind of pick that metric or several metrics. And of course, ideally show some animations, simulations. If you actually make something, working or non-working prototype, video, pictures, markup units, detailed drawings, anything that can give credibility to your idea. And the third thing is to perform this initial cost-benefit analysis. This should include some upfront capital costs, as many of you know, plus the operating variable costs. And this can be kind of a first step. In assignment 5, you will do this a little more carefully. In each case, of course, list your assumptions. And I know this is about a month away, so a little more than a month away, so you may not think about it, but these things take time, so I would recommend starting working on it soon. Another announcement, I just noticed that there's a free webinar from ComSol about camera design, so you can go here and register for it. Let's see if it shows up. Make sure the link's working. Yeah. So you can just register for it. This is ComSol. This is not the synopsis, but this shows you how to do the design of optics in a cell phone camera, for instance. And this is related to what Apratim talked about in his lecture, if you recall. So I think it might be very useful, and I highly recommend signing up for it. Okay, and the other things, so there's some interesting things here as well. NASA What's on the Moon challenge. This is kind of interesting because, you can watch the video and all that, but the idea is NASA's of course trying to establish a base on the moon, and we need power. So solar is the obvious choice. So there's some interesting challenges here. So I highly recommend everyone to read through this, just so you have a feeling for what some of the challenges are. Not particularly, I'm not gonna, it's not mandatory, but it's very, very interesting, and you can see what's going to happen in the future, and even in the near future, in the next decade, I would say. Okay, so let's come to our schedule. So today we are going to talk about, I just want to give a quick picture of where we are in the class. Today we're going to talk about radiometry, photometry, as well as some basic thermodynamics. Next week we'll talk a little more about some other applications, including recycling, anti-reflection coatings, and so on, and as well as measurement of photovoltaic. So quite a bit of material in the next 3 lectures. And then after that, we have the midterm. So we are going to post some example problems today, including some solutions actually. So you will have a chance to work through some examples. And also we have posted previous examples in the geometrical optics lectures. So you can go up here and see examples here as well. Let's see. Oh, I guess I don't. Oh, I guess I didn't post it. Okay, so I'll post them today actually. So you'll have them. Keep in mind the midterm is October 15th, so we're about 2 weeks out. And we're still trying to decide, but it'll probably be just timed 24 hours and it's open everything. So you will get the questions and you're expected to submit it 24 hours later. Of course, it's on honor system in the sense that I expect you not to collaborate with your colleagues because this is your work. I can't enforce that, so I'm going to, of course, but if it's obvious to me, that will be severely penalized if there's plagiarism. Any questions on the midterm before everyone? And everything up to here will be covered October 8th. Okay, October 13th is just a review, so it'll be essentially going through everything.
Oh, okay. So before the review session, do you maybe know what are the things we can maybe look into to just self-review?
Yes, so I would first say everything we covered until October 8th will be included in the exam. And the only thing that you don't need to include in the exam is the software. So things like the synopsis lecture as well as the COMSOL lectures, you can skip because I'm not going to ask you to design anything, although the concepts are important in there.
Okay, cool.
And you can actually go here and look at the review slides, which will be the same. This is from last year, but it will be the same this year. So you can see what are some of the points that are important.
Oh, okay. There's a sample exam from the last year?
Not sample exam, but some review slides of what topics are important, I would say. And okay. Of course, sample problems are there as well, as you can see on the link. Okay, and I'll post more sample problems actually today. And that's kind of the first half of the semester. Okay, so in the next, I know we don't have fall break, but just for purposes of planning, that the second half is starting October 20th. Okay. Any questions before I move on from this? Okay, guess not. And some of you asked about grades. I'll post them probably by Friday for the assignments. So if you don't see it by then, just remind me. And of course, use Slack if you have any other questions. Okay, so today we want to talk a little bit about a somewhat related topic to non-imaging optics, which is the idea of radiometry and photometry. Now, radiometry refers to things that we measure regarding light, and this can include power, intensity, intensity per unit area, all kinds of good things. Now, photometry refers to analogous quantities, but relevant to human beings. So how our eye perceives the light. So that's why radiometry and photometry are two distinct fields, but they are related. And photometry is a very complicated field related to not just physics or engineering, but also to human psychology. So it really depends on the perception from the human brain. And we're only going to touch a little bit of it so we understand what's important, for instance, for lighting purposes. So the day lighting team is something quite important that you need to keep in mind. And it's something you should know in terms of energy as well. So I want to spend maybe the first half of today's class on defining quantities and understanding what these things mean and how they fit into the perspective in an application perspective. So we'll start with this idea of radiation flux. So this will be a little bit of a review from what we have seen before. So we'll start with familiar things. Radiation flux is something you've seen before, because when we talked about the non-imaging optics, we had light energy coming from the sun from far away, passing through the CPC, and so on and so forth. So radiation flux refers to the quantity of energy that is emitted, transmitted, or received per unit time. okay, from a source. Now, if it's emitted, this is coming from a source. If it's transmitted, it can be from a CPC, for example. If it's received, it can be from to a solar cell or the human eye, right? So any of these are possible. Flux is, so by definition, it's the ratio of energy to time. And if you're talking about continuous variables, we'll take a derivative, right? So it's the derivative of energy passing through a system per unit time. Now, it's also called the radiant flux, and the units are, and it's also the radiant power, and the units are watts, which is joules per second, as we have seen before. Okay, pretty simple. Now, the analogous quantity in photometry is something called luminous flux, which is where the human being comes into the picture. So it is the perceived power of light by the human eye, which means that now we have to take the sensitivity of the human eye into account. Now, the humans have evolved over millions of years, hundreds of thousands of years, such that our eye is sensitive to the green light, which is here roughly, and it's about 560 nanometers in wavelength. And this is primarily because the amount of sunlight peaks at that wavelength, as we have seen before in our talk lecture on black body radiation. Okay, so because of that, our eyes, and we spend most of our waking hours during the day, our eyes are tuned to that wavelength. So this plot here gives us the relative sensitivity of the human eye as a function of wavelength. And of course, this is a representation. Every human is different, and every human sensitivity changes with time. So for instance, as you get older, your perception actually shifts around in terms of not just the sensitivity, but also your your resolving power of your eye. Since we have different sensitivities at different wavelengths, we cannot simply rely on the radiation flux, which of course will also change with wavelength, right? This is also a function of lambda in nanometers. But this by itself is not enough, because we need to account for the sensitivity of the human eye. And this is important, for instance, when you're designing a display for a phone, or when you're designing your lighting system in your kitchen, right? Or the automobile headlight. So it's important for many, many, many things, obviously. And this sensitivity is described by something called the luminous efficacy function, which you can see here in the blue curve, the bottom. And the colors are shown on the top, as you can see, which gives you a sense for, okay, what are the important wavelengths? And of course, we cannot see past about 660 nanometers or so. And again, this changes with your age. So if you're younger, you can see this. As you get to my age, you can't actually see this very well. And similar thing over here as well in the blue. So you get a sense for the range of wavelengths you're trying to see. This is also referred to as a photopic luminous efficiency function. There's lots of names to it, but just be aware that this exists. Now, this is also called the luminosity function, or the photopic luminous efficiency function, as we just said. This changes with the intensity level as well. And it's typically based on a normalized version. So, and that's the equation written here. So we have a dimensionless function here, V of lambda, which has no dimensions. And then when it's scaled by this number 683, you get the units of lumens per watt. And we'll talk about what lumens means shortly. But you can see the curve here shown on the bottom changes with the intensity. So we have scotopic curve, mesopic curve, and the photopic curve. Now, photopic curve refers to vision of eye under well-lit conditions. So this is under daylight conditions. So you can see the peak is somewhere here. The other curves are under low light conditions. And you can see it becomes more blue shifted. In other words, the peak wavelengths go to the bluer light. And the peripheral vision, which means your awareness of your surroundings are also become more sensitive at blue light, which is not shown in this curve, by the way, but just something to be aware of. This, I should just point out, this constant 683 here is not terribly important. It just comes from the fact that if you do an integral of this curve, any of these curves, for topical particularly, if you do an integral over all the wavelengths, so if I take this luminous efficiency function and integrate it over 0 to infinity, I should get 1. So it's just a normalization factor. That's what 683 is. Okay, we'll come to that again. So let me ask a quick question based on what we have done so far. Which street lighting is better for driving? And whether it's high pressure sodium lamps or metal halide lamps, one on the left or one on the right. And I don't want you to shout out the answers. I want you to think about this by yourself first. I'm not going to put you in breakout rooms quite yet for this particular one, but I want you to spend about 30 seconds or so. Think about which one is better. And then I will ask, then you can shout out, but let's give ourselves about 30 seconds. And of course, this is for humans, so for driving. Now, if you talk about autonomous cars, of course, this question is quite different, right? So we'll come to that also. Hopefully in 20 years, we don't need to drive. So any suggestions? And there's no wrong answer here, because you can make justification for either one. But
is it the one on the right, metal halide lamps, better?
And what would your argument be?
My argument is because on the left one, it's, even though it looks like it's warmer, it's like it's more light, it's yellow, like it kind of hurts your eyes. The one on the right's a little bit, how can I say, like it doesn't hurt my eyes when I see it. I don't know if that.
Okay, that's a good way to answer it. So you did an experiment on yourself. That's good. Anyone else? No. Okay. Let's go back to the previous slide. So first of all, we use street lighting when it's dark outside, so it's under low light conditions, right? So that means we need to look at these curves, scotopic and mesopic. Now you see what has happened here is that during the daytime, you can see your eyes are most sensitive in the green. But as you get to nighttime, your eyes become more sensitive in the bluish wavelengths, slightly bluish. So that means, of course, you want to light the scene where with colors of light where your eye can respond to with most efficiency. So you'll see more, essentially. Your signal is more than the noise, right? Signal to noise ratio is higher. So from that perspective, yes, you want the light to be more bluish. And you don't want a very hot white or warm white. You want a cool white. So this one would be the answer. So that would be one way to answer it. Now, of course, you can make other cases as well. For instance, the high pressure sodium lamps might be more efficient than the metal halide lamps. Actually, I don't know if that's true, but eventually you probably want to use LED. But you get the idea. So the color of the light in terms of the utilization of light is very important. Of course, the answer will be very different if you're talking about daylighting in an office, which by definition means that you have to work during the day, right? Because that's when the sun is out, and you want to essentially mimic sunlight because that's when your eyes are most sensitive. And we know from the daylighting team's presentation that that's when there's lots of productivity advantages if we try to mimic sunlight. Okay, this is a very simple example. So moving on, we know that a source is not most natural sources are not lasers. They emit at many wavelengths, right? Not just a single wavelength. So since sources emit at more than one wavelength, the strength of the visual sensation, you have to estimate that or calculate that, you need to do an integral. So the total visual sensation is represented by something called the total luminous flux, whose units are lumens, which we will see shortly. And that is computed by this constant 683, again, just a normalization constant, integrated from 0 to infinity of the source spectrum, which is this phi of lambda, which is in watts per unit wavelength. So this will be, for instance, the spectrum of the metal halide lamp, or the high pressure sodium lamp, or the sunlight, or whatever, multiplied by the sensitivity of the sun, of the human eye. Okay, so that's pretty obvious, right? This is how much your eye will respond. This is what is the source spectrum, and this is just some normalization. You integrate everything, you get the total luminous flux, which is the sensation, or the total visual sensation of the source perceived by a human. Okay, now let's try to define this a little more quantitatively. What is a lumen? A lumen is the unit of luminous flux. So it's the analogous radiometric quantities watts, right? Watts per meter squared, because wait, let's actually go back and make sure. Watts, sorry, not watts. So here, this is the radiant flux. It's analogous. This is the radiometric quantity in watts. And the analogous photometric quantity is lumens. It's a measure of the total amount of light emitted by a source. This differs from power, whose units are watts, since luminous flux takes into account the wavelength sensitivity of the human eye. First, in order to define what luminous, we need to define a candela. Candela is a unit of luminous intensity, which is power emitted by a source in a particular direction with the spectral sensitivity of the human eye taken into account. Okay, let's understand what that means. 1 lumen is equal to 1 candela steradian. Okay, lumen, so means that you have, let's imagine this is the human eye. How much watts are impinging on the eye? Okay, that is the lumens is a measure of that. Now, candela is a slightly different measure. It's a measure of how much watts is coming within a narrow angle. Within this little narrow angle, which we will define shortly, let's call it 1 steradian. How many watts of power are coming in? Now, of course, you're scaling this by the sensitivity of the lights of the eye, so it depends on the wavelength, but that's the difference. So lumens corresponds to the total here, whereas candelas correspond to a little slice of the solid angle. So if you integrate all the angles, you will get the lumens. Okay, so that's the conceptual difference. Now the definition of the candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency that's in the green, and by the way, and has a radiant intensity in that direction of 1/683 watts per steradian. And you can see that nice 683 number here, because as you do the integral, it becomes 1. You don't need to memorize any of this, but I just want you to understand this conceptually as I've drawn here. So if you think of a light source that uniformly irradiates 1 candela in all directions, so imagine a point source, and it is emitting light in all directions, right? Like into a sphere, just like the sun would, right? As we saw before. And just imagine if it was 1 candela, then its luminous flux will be 1 candela times 4 pi steradians, because 4 pi steradians is the solid angle of a sphere. Okay, you probably have learned this in high school. So it turns out to be about 12.57 lumens. Now a candela, we'll look at what these things look like in an actual system in a few minutes. Let's try to do a quick example here, and I'm going to break into breakout rooms, and I want you to discuss how to solve it. Okay. By the way, I have a question for you. When you go to breakout rooms, can you still see my screen, or does this disappear?
We cannot, I think.
Okay.
No, we
cannot
cannot see the screen.
It disappears. Yeah.
It disappears. Okay, so that's it's a problem with the Zoom. But nevertheless, you can try to remember this or write this down conceptually. Before I put you in breakout rooms, this is a question I want you to discuss. What is the maximum luminous flux of an LED whose luminous intensity is 1 millicandela? Okay, so luminosity intensity is 1 millicandela. What is the flux? It should be relatively straightforward. So you can think about this. I'm going to put you in breakout rooms. Joseph and Abdullah, are you not able to join? I can't hear you guys. You're on mute. You can get it if you want, but. Okay, welcome back, welcome back. Some of you were not able to join, so hopefully it was not a technical issue. 30 seconds. Anyone have some interesting answers? Or at least how to address the question?
Yeah, I think we were just talking about how if we don't have the, because I guess we're assuming that the LED was also uniformly radiating.
Yes, good question.
Yeah, so we just assumed that, and if the intensity is 1 millicandela, then we pretty much just, in that equation above, just replace 1 CD with 1 over 1,000 CD. Which would come out to 0.01257 lumens.
Great. Yeah, no, that's definitely a good way to think about it. Now, however, we do know that the LED does not emit in all directions, right? Because LED is made on a chip. And it looks like that typically, and it has some packaging and stuff. And so the most it can emit is actually only a hemisphere.
Okay, well, in that case, we would just divide it by 2.
Exactly.
Yeah.
So just be aware of that. Now, of course, this is strictly not true because there are many companies which are also trying to, because this part of the light, it does emit in this direction. This part of the light is essentially lost. There are lots of companies which are trying to capture that to increase the efficiency of the LED. Now, by the way, this the development of the LED was, of course, a subject of the Nobel Prize a few years ago, as many of you know. So, of course, you can write down the equations. The solid angle of the hemisphere is 2 pi steradians. And so the intensity is simply 1 millicandela times 2 pi. Okay. So again, I don't.
Professor, I didn't understand. Why is it 2 pi if we're just getting 180 degrees right there?
Yeah, so this is a sphere in 3 dimensions has total angle of 4 pi steradians. And here, what we have is half of a sphere.
Gotcha. Okay.
So, the light's going downstream in this example. So this becomes 4 pi divided by 2. Just be aware of what I really want you to get out of this is really understand the concept of what is intensity and what is flux. Okay, intensity refers to per unit solid angle, whereas flux refers to the total. And of course, a very simple example. Let's do a little more complicated examples, I guess. So before we do that, we need to understand what is a lux. Lux is another unit which we are not typically very familiar with, but it is the SI unit of something called illuminance or luminous emittance. This is luminous flux, which is what we just saw, per unit area. Okay, so it's lumens per meter squared. So 1 lux is 1 lumen per meter squared. And this is equivalent to intensity as we would normally talk about in radiometric optics. And 1 lumen is, of course, 1 candela steradian. So 1 lux is 1 candela steradian per meter squared. Okay, so now I'm gonna put you into breakout rooms again, and I want you to try to answer these 2 questions. So you may want to write this down before you get disconnected. Let's say we want to achieve an illuminance of 500 lux for a home kitchen. What is the minimum required luminous flux from a single fluorescent light? Okay. And the second part of this question is, what if we want to light a soccer field? Okay, I'm going to put you in breakout rooms and let's take about a minute. And definitely try to discuss with your peers. That's the whole idea. And this is how we learn. So it's okay, you ask all the naive questions now. Are you guys okay with the question? I don't hear anyone talking, so. Okay, sorry, I had muted myself. So.
Yeah, so we want to achieve a luminance of 500 lux for a home kitchen. What is the minimum required luminance flux for a single fluorescent? So 1 lux is 1 lumens per meter squared, right? And we want 500 lux. So don't we need to know the area of
Okay, were you able to discuss it all? Carl, Nguyen, or Wei,
Huh?
as you guys are back. How would you solve this problem?
So we just times the areas.
Sorry, what times area?
500 lux.
Yes.
Just use like the illuminance times the area, like pitching
Yeah.
area, soccer field areas.
Right. That's correct. And I want you to get a sense for the scale. So a typical LED light puts out 50 to 100 lumens. So how much do we need? So the area of the kitchen is, of course, I need to give you the area. So the area is not given, so you can assume. So it's 100, let's say 10 meters squared. The luminance is luminous flux divided by area. So the luminous flux is illuminance times the area. So we want a luminous flux of 500 lux. Illuminance of 500 lux, 500 times 10, say 5,000 lumens. Now keep in mind that the typical LED puts out 50 to 100 lumens, so that from that you can figure out, okay, you might need a massive fluorescent light or many separated LEDs. If you want to light a soccer field, of course, you have to scale everything accordingly. So gives you some rule of back of the envelope calculations on the numbers. The other radiometric quantities that we want to know are a few things like emittance, which is just different terms for the same thing to some extent. It's the radiation flux emitted per unit area. So it's emitted from a source like the sun. So it's watts per meter squared. If I over dA, irradiance is the radiation flux falling on a surface. So in the case of, for instance, a solar cell or a hot, absorber for heating water, for example. The corresponding photometric quantity is illuminance. The units are lux. And the intensity itself is defined as flux per unit solid angle, which is watts per steradian, shown here. And the corresponding photometric quantity is luminous intensity, which will be lumens per steradian. Okay, all of these now starting to become more familiar. So there is per unit area, per unit steradian in radiometric quantities, and then also in photometric quantities. Now, the radiant intensity is defined in the direction. So the direction of in which you're measuring this is very important, because you could have a source that is not emitting the same in all directions, right? Which is what we saw in the two examples before. Radiance is radiation flux per unit projected area and per unit solid angle. The projected area means normal to the direction you're measuring, okay? So it's defined as d phi over dA cos theta d omega. This dA cos theta gives the projected area. So you can see in the schematic down here, this n represents the surface normal to this surface here, whose area is dA, and this is the direction in which you're measuring where your detector is, and theta is the angle in between. Then dA cos theta is simply the projected area normal to the observation direction. And this d small omega is the small differential solid angle. So that comes in here. Okay, so this should be relatively straightforward. And you can define the corresponding photometric quantity as luminance. So again, we know how to go from here to here, because you have to account for the visual flux, which is the sensitivity of the human eye. And here you went from watts per steradian per meter squared to simply candelas per meter squared, because watts per steradian is a measure of candela. Or it can be lumens per steradians per meter squared. Now, radiance and luminance are functions of wavelengths, not can be, so this should be R. Then we can define spectral radiance and spectral luminance, which means they are simply this L is now a function of wavelength, so you have to integrate over all the wavelengths to get the total flux. And the same thing goes with the spectral luminance, where the small v refers to the fact that we have to take the sensitivity of the human eye into account. Now we know we can relate these two things, radiometric and photometric quantities, by this relatively simple integral, where you are accounting for the sensitivity of the human eye. That's what this is. And some normalization factor, okay? And that's true for all the analogous quantities, by the way. Radiation intensity emitted by an area dA is now given by d phi over d omega, which from this expression, this expression here, will give us L cos theta dA. So remember, dA cos theta was the projected area, and d phi d omega is now the watts per steradian, or lumens per steradian, as candelas per lumens per steradian, sorry. Now, if you assume that the radiance is uniform over an area A, so this area of the source or the detector is uniform, or the radiance is uniform. So in other words, the source is far away from a detector. This is the case of the sun, for example. Then total intensity in a given direction is simply that integral. And this cos theta simply comes out of the integral because you're simply integrating the area A, and then you get L cos theta A. Okay. Now, L itself can be a function of theta, which is the direction in which the light is being emitted from a source. So that's why you have to put that as in the function here. But in case the L is independent of direction, if you assume an isotropic emitter, in other words, a source that's emitting equally in all directions, which for instance, in the case of the sun, this is what we assume, then we can simply drop the theta. And then we can also say I naught is L times A, which is the normalized radiance. And we get a very simple expression, something referred to as Lambert's law. I equals I naught cos theta, okay? Which simply says, if you look, if a surface or source can be Lambertian if it emits or receives radiation with an angular intensity pattern that follows Lambert's cosine law, it's solely dependent on the projected area. So it's typically represented like the following. So here, this is intensity represented by the length of these arrows, and the angle, which is the angle of the arrow, this angle is the angle in which you're looking, or the light is being emitted. So normal direction on axis is 100%, which is cos theta is 1 now, right? And cos theta is decreasing. If at 90 degrees, cos of 90 degrees is 0, right? So you can see this is Lambertian. The size of this arrow is decreasing as you go to larger angles. Now, all of you are actually looking at a Lambertian source right now because you're looking at your LCD screen. Now, I would encourage you to do an experiment. Go off axis from the LCD, right? So I'm actually doing this now. I don't know if you can see my video, but if you go look at your LCD from a very steep angle, you will see that you are reducing the intensity that you're seeing, right? It will get dimmer and dimmer and dimmer. Most good LCDs actually come with a very wide viewing angle. So this effect is sometimes not so pronounced. In the case of the phone, for instance, it'll be more pronounced than you would on a laptop. And some of you are familiar with privacy screens where you try to increase this effect. In other words, you only can see it if you look in a very small viewing angle. So these things are quite important. A surface, a Lambertian surface, can also be diffuse or specular. And this is examples of that. And you can, all of you know what it means by diffuse or specular, but this can also be represented by something called by the Lambertian law. So the diffuse would be a Lambertian surface, where the specular is not necessarily a Lambertian surface. Now, these are important in computer animations, as some of you are probably aware of. So this is the model for what you're seeing on the left-hand side. So the incoming light is coming at some specific angle. If it is a diffuse reflector or Lambertian reflector, the light reflects in all directions. But if it's a specular reflector, then light just reflects off following the law of reflection. So that would be a mirror, right? A mirror is specular. Okay. A Lambertian emitter, in the case of a LED, is also very important from a practical perspective. And there are many different types of LEDs. You could have an LED that's planar, where the source is embedded inside some semiconductor, and then the angle of emission is determined by the escape angle or the critical angle of the LED, right? So if the refractive index of the semiconductor is 1, then we know that the largest angle that you escape from the LED is defined as sine inverse of 1 over n, right? This is the critical angle defined by the total internal reflection, because anything larger than that will be trapped inside the semiconductor. Now you can capture more of the light out by simply curving the packaging of the LED. So sometimes you often see the LEDs which look like that, right? The LED leads coming out, and then there's some sort of plastic curve, and that gives you an idea of a bigger angle of emission. You can also make it parabolic, which gives you a more collimated emission. So these are represented by something called these polar plots, which is, again, in the horizontal axis is the theta, the angle of emission, and the plot in the, oh, sorry, actually my mistake. This is actually not theta. This is normalized intensity. So it goes from 0 to 1. And this angle in this direction is a theta, just like before. So on axis, you get the maximum. And then as this curve, for instance, goes down at larger angles, at 10 degrees, you're getting a slightly less. So the length of this arrow from here to here represents the intensity. And you can see it going down. And even at very large angles, in this case 90 degrees, you can still get about 0.2 of the light in the case of the parabolic LED. In the case of a Lambertian, of course, it goes to 0. As you can see, it's a circle, right? That's a Lambertian, which is an example of the planar LED. And the hemispherical LED is the perfect hemisphere, the outside curve. And you can derive all this pretty easily. So let's do a couple more examples. So the first example, let's zoom in here, is a point source. A small point source emits light equally in all directions with radiant power of 10 watts. And I'm going to put you in breakout rooms. I want you to write this down. Total radiant power is 10 watts. What is its radiant intensity? And what is its irradiance at a distance r? So let's, now just to remind ourselves, actually, I'll have you discuss first. Okay, perhaps that was a little too quick, but so you will have to review that example. So the answer is there, but let's just review. So there's a point source that emits equally in all directions, so it's isotropic with 10 watts. And this is what you would expect. It's emitting in all directions. See, not everyone's back yet. Okay, everyone's back now. So, okay. It's emitting in all directions. So it's 4 pi steradians. So 10 divided by 4 pi watts per steradians would be the radiant intensity. Okay. Again, my idea here is just for you to conceptually think about these simple problems, because we're going to increase the complexity later on. Now, irradiance is power per surface area. So you need to understand what these things mean. Radiant intensity is power in that unit angle. So again, keep in mind my picture that I drew some time ago. If you have light, so flux is everything, whereas the intensity is only within a small solid angle, right? So that's the first part. The second part is power per surface area. So you need to know how far away it is. So if the distances are, this radiant intensity spread over an area of 4 pi r squared, right? So 10 watts divided by 4 pi r squared would be the irradiance. Okay. The next question, let's increase the complexity a little bit more. So let's imagine we have a flashlight. Okay. So we have a radiant power of a bulb with 200 milliwatts being emitted. What is the radiance at a distance 25 centimeters from the flashlight's front window, and what is its radiant intensity? So I'm not going to put you in breakout rooms for this in the interest of time, but let's think about this together. So the bulb is emitting 200 milliwatts. Okay, and that's in all directions, presumably. I haven't given you that, but let's assume that. What is the radiance at a distance 25 centimeters from the front window, which is shown here? So that's the front window, is 25 centimeters. So we will need to understand irradiance is watts per meter squared. So we need to understand what is the power over a circle that far away, right? And then divided by the area, the times the subtended area. So the subtended area is shown here, which is 10 centimeters, and you, from that fraction, you should be able to figure it out. And what is this radiant intensity? Irradiance would be per unit solid angle, and the radiant intensity would be when you times it by the area. So I'll leave that as a homework problem for you to work out in the interest of time, and we can talk more about it if you have questions. Post them on Slack, but I would highly encourage you to try to solve this yourself. Before I move on to this, I want to show one quick video about visualizing what the different units, lux, lumens, and so on mean. So let me see if I can find the video. Not this. It's this. Let's see.
In lighting, there are 5 descriptions or terms that we use, metrics
don't know why
we call
it's
them,
tilted.
to describe the light. And I'm going to just demonstrate them for you now. If you take a look at the candle, this is our original light source. The candle is actually emitting an intensity in all directions. And that intensity is actually 1 candela, which is about the amount of light you get from a candle in any and all directions. This unit of intensity is used to describe the light output from any light source. So I take a light source like my flashlight, I aim it at you, you see a much greater intensity compared to the candle than as I vary the angle at which you see it. So this is basically the beginnings of a simple photometric test in trying to describe the light output from any light source, in this case a simple flashlight. The second unit of measure is flux, which is the light which flows in air. To talk about that, I'm going to use this frame. This frame is carefully chosen to be 1 square foot, and I'm holding it 1 foot from my source with an intensity of 1 candela in all directions. In this definition, what I have is 1 lumen of light flowing through this window. and that's the flux of energy flowing from this source. Now, it's not hard to imagine that there are other frames out of which this light can flow. In fact, there would be 12.57 lumens of light being emitted equally from a source of 1 candela intensity, 12.57 lumens
We of course did that
flux or
calculation.
light flow. So we talked about flux being the unit of measure for the flow of light, and my question to you is, does light flow? So the answer is the light flows from this source of light through this frame. You see the shadow in the wall. You see when I move the frame, the shadow also moves. This tells us that, in fact, light as a form of energy does flow. The question, at what speed does it flow? At the speed of light, of course. The third unit is illuminance, which is the density of light that falls upon a surface. When I consider a surface instead of a window that is 1 square foot, and I have a source with intensity of 1 candela, in fact, I have 1 lumen of light falling upon the card. The density of light on this surface is a foot candle, 1 lumen per square foot. Why do we talk about foot candles? It's because foot candles are actually cheaply and inexpensively measured. So with a simple device like a light meter, I can measure the density of light falling upon a surface. So if what we said is true about foot candles, using our light meter and a flashlight, if I hold the flashlight a certain distance from the light meter, I get one reading, but as I vary the distance from the meter, the numbers slowly
And this was the
decrease
example problem
as a
we
function
just saw.
of
Right.
the distance, reducing the density of light on the foot candle meter. Same too with angle. If I start at a certain angle and I try to keep the distance the same but vary the angle, the numbers also go down. So we understand that foot candles, or the density of light, varies as a function both of distance and also of angle of incidence of light. These two things are accounted for in both the equations that we use for determining illuminance. There are two things that impact that density of light, and I can demonstrate them going back to my flashlight and looking at the wall. If we consider a circle on the wall, there's a certain density of light falling on the surface, the illuminance. As I increase the distance, you see that the light is actually covering a much larger area. Therefore, the density of illuminance, the foot candles, are being reduced as I increase the distance. This is called the inverse square law because it varies in
Yeah, so we know
inversely
this is
to the
why
square
Earth
of the
gets
distance. It
much
also
more
varies,
light
however,
than Pluto,
with the
for
angle at
example.
which the
It's
light hits
closer
that
to the sun.
surface. And you see that as I increase the angle, the light is covering a much greater area. And looking at the very center point, I can practically project that across the entire wall. The density of that light, therefore, is greatly reduced as a function of the cosine of that angle. We'll revisit this when we talk about calculations. The fifth way of talking about light is the light which comes off of surfaces. And let's consider our card again. 1 square foot, 1 lumen of light falling upon 1 square foot or 1 foot candle. Now let's talk about the light coming off of this surface. That would be a function of the reflectance of that surface. Looking at a white surface, we have certainly more light coming off of this surface from our candle compared to this surface, which is in fact black. The only difference between the two surfaces are the reflectances, and this is referred to as the excitance. How much light is coming off of this surface, or the density of that light coming off of a surface? It's largely a function of illuminance times the reflectance, and that's what excitance
We didn't talk about that,
but that's not the end of the story, because when I change the surface again to one which has a different reflecting characteristics, I get quite a different effect. So even though perhaps this card is 95% reflective, and perhaps this surface is also 95% reflective, a mirror. So the total amount of light, or the excitance coming off these surfaces, are the same, but the way in which light comes off of these surfaces is very, very different. And this is a function of the specularity of the surface. And this is what we call luminance, the specific way in which light comes off of a surface. It's luminance which allows us to see things. It's the luminance which enables our ability to see the world. And it's luminance that we really try to control as we design light and architecture.
Okay, so you got an idea of the importance of these concepts. The last part I want to talk about in this lecture is color. Color is, of course, a very complex topic because it's a perception. So there's a physiological basis of color, but also there's a psychological basis. So physiological basis is somewhat easy to explain. We have four different types of cells in our retina which respond to light, and they have sensitivities that are different. So there are blue cones that are more sensitive to blue light, green cones that are more sensitive to green light, red cones that are sensitive to red light, and then there's something called rods, which are more sensitive to all light to some extent, but works under low light vision. So cones are for photopic vision, where it's nice illumination. Rods are for scotopic vision. So quite important. Color can be created by addition of wavelengths. So if you, this is an example from an old television set, for example, you had 3 different colors which are mixed together. So you have red plus green plus blue can create white. So it's addition of colors. And of course, you can have addition of different kinds of colors. So in this example, all the colors of the rainbow create the red. And here we are missing the green part of the spectrum. And then you create some, which looks like cyan. Right, so those are examples of how you can create different types of colors, which of course is very, very important in displays, as you probably know. Colors in displays are created by subtraction, not by addition, because of the nature or the physics of the liquid crystal that's used in a display. And many of you might be familiar with it, but let's just review. In a display, we have something called a backlight, okay, which is essentially an LED with it's usually a blue LED with a yellow phosphor. We don't need to really understand the details here, such that when they add up, you get white. Okay, and white light comes in, and there's a polarizer that polarizes the light. Then there is an electrode which controls the liquid crystal. And there's another electrode here. So between these 2 electrodes, there's a capacitance that when you apply a voltage can rotate the liquid crystal. So if you don't apply a voltage, the liquid crystal stay down like that. But when you rotate, they rotate 90 degrees as shown here. And the liquid crystal essentially rotates the polarization of the light. So if they're staying down, nothing happens to it. The polarization remains the same. And then we have a cross polarizer here. This means that this polarizer and this polarizer have orthogonal axes. So this polarizer might be polarized this way, and this polarizer might be polarized in the orthogonal axis, such that if nothing happens to the light, then no light comes out. So that looks dark. Now there's a color filter here which absorbs, so this allows blue to pass through, absorbs green and red. Here, red and blue passes through, green is absorbed, and here red is passed through, green and blue are absorbed. So in this example, where we have rotated the polarization only of the red pixel, this pixel looks red. So where I'm coloring right now, this part of your screen is doing exactly what's shown in the schematic. Only red is passing through. Okay. Now, can anyone tell me what is a problem with this approach? Anyone?
No idea.
What's the problem that you have faced with your phones recently, other than internet connection? Has anyone ever run out of battery?
Yes.
Okay, so one of the main reasons you do is because your display uses a lot of power. That's a hint. So one thing to think about is you are throwing when I say this light is lost, you're essentially throwing that away, right? You're coming with 100% of light, and here you can see I'm coming with 1/3 of the light, right? What happened to the other remaining 2/3 or 70%?
Lost.
Is lost. Exactly. So that's a very poor way to do designs or displays, but this is how the vast majority of displays are done. So that's a very important problem, right? If you can solve it, you'll make a lot of money. So I'm not going to show you a solution, but actually, if you have time, I'll show you a potential solution, but no one has actually solved it, except most recently we have OLEDs. In the case of OLEDs, it's an organic LED, which means that instead of having a light valve like the LCD, you simply have little points of light that emit the light, and then it's much more efficient. Okay, we won't talk about it, but that is the solution. But OLEDs are, of course, much more expensive and so on. They have other trade-offs. So is there a better way to do this? And that's the video that I will show you shortly. But before we talk, actually, maybe it's a good time. Talk about that video quickly. And hopefully this is in the right orientation, and I'm going to fast forward this.
Panasonic has developed a unique
So
technology
this is some
that
work
doubles the brightness of color
Panasonic did
photography
a few years ago.
by using micro color splitters instead of conventional color filters in the image
So
sensor.
this is in the image camera.
These two
let me
photos
pause
were
it.
taken using CCDs with the same sensitivity.
Ah.
The one on the right.
Okay, so this is not a display, but the technology is the same. In the case of a camera, you have an image sensor. So instead of, you have a similar kind of a principle. So what's happening here is that here only 30%, oh, I can't write on it, sorry. On the right-hand side, you can, only 30% of the light has passed through because it's a conventional approach. On the left-hand side, they are using a new approach where you're getting almost 100% of the light. And in the case of a camera, you can see that the brightness of the image is much higher.
It was taken with the color filter system used in nearly all digital cameras.
And they'll explain the
And
concept
the one
shortly.
on the left was taken with Panasonic's new micro color splitting system. Until now, image sensors have produced color pictures by using red, green, and blue filters for each pixel. But with that system, 50 to 70% of the light is lost.
今回はカラーフィルターを用いない、その結果として光の損失なく光を取り込むことができる。かつ CCD とか CMOS または BSI といったいろんな種類のセンサーが提案されていますけれども、その種類の
Okay, so I will summarize. This is talking about the image sensors, which are not particularly important for us. But let me, some reason my iPad is slow. Let me see if I can fast. So the way this works, that's the important thing I want to show you. Yeah, that's explained.
Reaching each of the 4 pixels. For example, if white light enters each pixel, pixels where it doesn't pass through a deflector receive unmodified white light. But in pixels with a red deflector, the light is split into red diffracted light and cyan non-diffracted light. And when white light passes through a blue deflector, it's split into blue diffracted light and yellow non-diffracted
So
light.
you can see the color is created by
result,
not absorbing
the
the
arrangement
light.
is cyan,
You're simply
white plus
adding
red,
the light.
white plus blue, and yellow. The RGB values are then calculated using a processing technique designed specifically for mixed color
so of
signals.
course in a display you can't really quite do this, but yeah.
To design the microcolor splitters in this way, it's necessary to analyze optical phenomena such as reflection, refraction, and diffraction in 3D. Analyzing various wavelengths of light for each form of microcolor splitter.
So here they're
high-speed
using some fancy
computation,
algorithms to do the
practical until
calculation,
now.
which is similar to what you guys already talked about the last few weeks. Let's see, I think that's the basic point I wanted to make. So let's come back here. Okay, so there's still lots of innovation happening. By the way, that technology is not still commercialized yet. So that video was from maybe 5 or 6 years ago. So it's still quite active area of research. So colorimetry is how do we quantify color? So for example, if you come up with a new display technology, how do you compare that to an old display technology and say, oh, here you go, my innovation is fantastic. So you have to have some quantitative way. So this is, we're going to talk very briefly about how to do that. Of course, because color perception is psychological, not purely physiological, it cannot completely explain everything. So, but there is a theory called the tri-stimulus theory, where every color can be described by 3 numbers, which quantify the stimulation of the red, green, and blue cones in the human eye. And this is also referred to as the CIE acronym for the French Commission, the French name of the commission that actually developed this. based on something called the XYZ color matching functions. Okay, this is relevant to the human eye sensitivity as before, except that now we are responding to the 3 different colors. So those, the values, the 3 coordinates are calculated by this integral, where the integration happens in the visible band, 380 nanometers to 780 nanometers. And the integration is of a function I of lambda times X of lambda. Now, I of lambda is the input source spectrum. Okay, this is whatever the backlight of the LED times everything else, the polarizers, the LCD, whatever, in the case of an LCD display. X bar lambda, Y bar lambda, and Z bar lambda are standard curves, which are shown here. Okay, and they represent the blue part of the spectrum, green part of the spectrum, and the red part of the spectrum. So that gives a value for these 3 values for the color, and they're plotted in this curve, which is referred to as a chromaticity diagram. Of course, it's a 2-dimensional curve, so you have to take those 3 numbers and represent it with 2 numbers, and that's shown by these equations here. Okay, so it's an average of the X and Y, and that's plotted in this 2-dimensional space, whose values now correspond to certain colors. Now, of course, this is not a unique representation, just so you're aware of it. But you can see in this plot, the envelope of this plot, or this outside, this line here, for example, the outline of this plot represents pure wavelengths. So, for example, this point here is of exactly 520 nanometers. This is exactly 540 nanometers, and so on and so forth. And anything in between is a mixture of spectra. So the outline of this plot is only possible with lasers, very narrow sources. So it's not realistic in a display unless you're talking about a holographic display or something very special. But otherwise, you will be talking about mixtures of wavelengths which create these colors. Okay. And they're also called the projected coordinates XY because you're taking the XYZ3 coordinates and projecting into a 2D plane. Also called the CIE CY color space or chromaticity diagram. Again, you don't need to memorize any of this. Just I want to make sure you understand conceptually what these things mean. And that's it. That's basically the end of this part of the lecture. And let's see, are there any questions before I move on? So the next lecture on thermodynamics, I don't want to quite start it. It's fairly short, but I want to show 2 videos before we end today, so you have a motivation for why we want to understand this. So I'm going to actually open up those videos first, and they are important. So let me close that. Okay, so this, I'll just show the one video first. So I assume many of you have driven from Salt Lake to California or to Las Vegas or flown. You probably have seen this on your way. It's right next to the highway, something called Bright Source. It's in a town called Ivanpah. I think it's just outside Las Vegas, near the border of California and Nevada. It is the largest what's called the solar power tower in the world. So you can see, now I want to just play the video first. So if you have never seen it, it's an amazing sight, especially if you fly. So try to get a window seat on the right-hand side, I believe, when you fly from Utah to California or to Nevada, for example. So let me just play this first. So you can see that this is just a picture of the video of the construction. They're constructing the solar tower, which is the central part where you are going to direct the sunlight and heat up. There's a black body, which is black, of course, and then it gets very, very hot, and then you flow fluid through it typically, or a salt that melts because the temperature gets so high. And it's pretty massive. and you will see they're going to lay down the heliostats. So those heliostats are essentially mirrors that track the sun, which you can see on the ground there. And as the sun moves across the sky, these heliostats will adjust their angle such that the sunlight is essentially directed or kept directed at the hot spot. And it's pretty massive, so you can actually see it from the air, and if you drive by, you can actually see these things. I don't have a nice picture of the system working, but in the next class I can show it. But you get the idea. So this is an example of a system where we need to understand the thermodynamics of solar thermal devices. So again, the picture here is quite simple. So we have the sun, sunlight comes in, we have a mirror, and then we have some sort of a black body that's absorbing the light, right? And then you have a lot of mirrors, and the location of the mirror, the angle, this angle is different than this angle. And this is referred to as a heliostat. Okay. We'll stop here today because we covered a lot of material, and I don't want to kind of overwhelm it with too many things. So stop and see if there are any, whoops, any questions.
No.
Okay, wonderful. So again, two important announcements. Make sure you start working on the midterm, which will be in 2 weeks, October 15th. And the assignment 4, which is due roughly in a month. I'm going to change it for November 3rd because of elections. So, but it'll probably be the next Thursday, but I'll post it and make an announcement on Canvas. Great. Well,